We're going to be taking a look at today the binomial theorem. The one time in the school year I get to teach you a shortcut. It's going to speed up your I know, yay! It's going to speed up your process of evaluating and working with binomials raised to powers. It might come in handy when you're dealing with transformations. You may be seeing a connection between working with permutations and combinations, which is some kind of topic related to probabilities. Let's start off with doing this. We've got a plus b raised to the 0 power. What's that going to be equal to? Yeah, anything raised to the 0 power is 1. We've got a plus b raised to the 1st power. What's that going to be equal to? Well, duh. Yeah, it's just a plus b. We've got a plus b squared. And since we're in the last quarter of pre-calc honors, or maybe possibly third quarter, depending on if we have hurricane days or not, a plus b squared, what's that going to be equal to? Yeah, it's going to be a squared plus 2ab plus b squared. All right, so take a minute and figure out what a plus b to the 3rd power is, please. Foiling acronym does not work with trinomials, so how about we just try distributing them together? What is a plus b cubed? How about a plus b to the 4th power? It's a to the 4th plus 4a cubed plus b plus 6a squared b squared plus 4ab cubed plus b to the 4th. All right, we got that down pat. How about take a minute and a plus b to the 5th power. Let's figure that out. All right, so you're distributing a plus b through, we're just doing recursive work. You don't even have to start from scratch. You don't have to write 5 of these factors and do all that distribution. You just have to multiply a plus b to the 4th times a plus b. All right, who's got an answer? Anybody? Nobody? Come on, you're just multiplying a 1, 2, 3, 4. You're just multiplying a 5-term polynomial with a 2-term polynomial. So your ab to the 5th is going to be a to the 5th plus 5a to the 4th b plus 10a squared cubed b squared. Wake up, Taru. Plus 10a squared b to the 3rd plus 5a b to the 4th plus b to the 5th. Okay. Scanning. Perfect. All right. Come on, I'm hoping somebody steps up and gives me the answer here. A plus b to the 6th. Figure that out. What is the next line here? A to the 6th plus what? Plus what? 6a to the 5th, b to the 1st. Okay, well, you got it started correctly. What's the next term? How did I write a plus b to the 4th and a plus b to the 5th, at least when I wrote it correctly? How did I write down the answer so fast? There must be some pattern up there. The last one is b to the 6th. The 3rd term is plus 15a to the 4th b squared. There will be a 15a to the 2nd b to the 4th. It's going to be 6ab to the 5th and a b to the 6th. We're only missing one more term. We're at, what is it?
28 to the 3rd.
Okay. And of course, we can keep this going on and on, but I want to do more than just a couple of examples. So there's got to be something going on here. When you do a binomial raised to the 6th power, there is no reason for you to have to write out 6 binomials and do all of that repetitive distribution process and adding of like terms. So where did the 1, 6, 15, 20, 15, 6, and 1 come from? Well, every single first number in each row has a coefficient, and every last term in each row has a coefficient of 1. We've got we don't have a second term here, but our third term has a 2, and then our second term has a 3, and our second term has a 4, and our second term has a 5, and our second term has a 6. So there's something going on there. Anybody see where these numbers are coming from? Where did the 15, where do you think the 15 came from? Where did the 6 come from? Do you see it just as 2, 3, 4, 5, and 6? If you're going up by 1, what are you adding by?
Well, I was going to say, the 6 came from the 1 and the 5 above it.
Yeah.
The 3 came from the 5 and the 10 above it.
The 3 came from 2 plus 1. The 4 came from 3 plus 1. The 5 came from 4 plus 1. And if you just go down sequentially on the sort of like diagonal, there is an addition of 1, but there's another place you find 1 in the previous line of work. It's 1 plus 2 is 3. It's 1 plus 3 is 4. It's 1 plus 4 is 5. It's 1 plus 5 is 6. So yes, it's 2, 3, 4, 5, 6. Yes, we have an arithmetic sequence where we're adding by 1, but in terms of this 6 coming from 2 numbers in the previous row, it's 5 plus 1. It's 5 because it's 4 plus 1. It's 4 because it's 3 plus 1 and 2 plus 1. And this 2 is coming from 1 plus 1. So let me ask the question again. Where did this 15 come from? It came from 5 plus 10. And this 10, therefore, came from 4 plus 6. And this 6 came from 3 plus 3. This 3 came from 2 plus 1. The 4 came from 4 plus 1. The 5 came from 4 plus 1. The 6 came from 5 plus 1. The 15, so every new number, okay, every new coefficient that I haven't read, it gets a little dark because of writing over the black ink, but every coefficient in, some line of this triangle is the sum of the coefficients, the sum of 2 coefficients just above. And they come together in like little, almost like triangles, if you will. So then, what is going to be a plus b to the 7th power? 1a to the 7th, and then 1 and 6 is 7, so plus 7, a 6th, b 1, plus what's 6 and 15? 21, so plus 21, a to the 5th, b squared. What's 15 and 20? 35, so plus 35, a to the 4th, b cubed. And I really want to just stop and go on to something else, but I got this started now.
Thank you.
20 and 15, another 35, so plus 35, a to the 3rd, b to the 4th. 15 and 6 make 21. A squared, b to the 5th. 6 and 1 make 7. A, b to the 6th, and then finally we have a b to the 7th, and I'm taking a lot of time up with this expansion, so let me stop. Did I make a mistake? Is that all good? Okay. So, in red, what we have, the 1, 7, 21, 35, 35, 21, 7, and 1, all the red coefficients, except for the last line, I'm not going to write that again. That's called Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on and so on. That Pascal's triangle can be made very rapidly. And these translate into coefficients of when you raise a binomial to a power of 0. The coefficients when you raise a binomial to a power of 1, and a power of 2, and a power of 3, and so on and so on. Now, while that's super cool, if I ask you a question that deals with a binomial to like a power of like 25, you may not want to write 26 lines of Pascal's triangle. So Pascal's triangle is awesome for doing an expansion of a binomial raised to a, maybe a single digit power. Or you just want a complete expansion period. What else do we see in the pattern? What else do we see like in terms of the exponents? There's some other additional power going on. Like, what did I do? We'll never, yeah, make your observation, sir. Yeah, so let me do something that's a little bit higher up so we can all see it. So when we have a power of 4, the first term is a, and a has a power of 4, 3, 2, 1, and then there's no base a, so that basically is an a to a power of 0. So the power that goes on the first term ends up being the same power that you apply to that binomial. So we have an exponent on the first term going down by 1. And as soon as like a plus b to the fourth, we have an a to the fourth, all of a sudden in the next term, a b shows up. So you might want to think of this as 1 times a to the fourth, b to the 0. And then you have a 4, a to the third, b to the first. And then you have an a squared and a b squared, then you have an a to the first and a b to the third, and then your last term here, like on your a plus b to the fourth, you might want to think of this last term, at least in terms of notes, as not 1 times b to the fourth, but 1 times a to the 0, b to the fourth. So the first term in your binomial will have a power that is going down. The second term in your binomial is going to have a power that goes up. And what is the sum? Again, let's focus on this ab to the fourth. What's the sum of 4 and 0? 4. What's the sum of 1, 3, and 1? 4. What's the sum of 2 and 2? 4. What's the sum of 1 and 3? 4. What's the sum of 0 and 4? 4. Okay. What math operation, what math symbol have we recently learned that creates a whole lot of additions? Sigma. So a binomial a plus b raised to a power of n is going to be equal to, we have a Greek letter of sigma coming in to show that we're going to create an expanse of additions. A bunch of terms being added together. And, as a formula anyway. The upper limit is going to be n. And these numbers in Pascal's triangle, each of these numbers correlates to something called a binomial coefficient, which later on in mathematics you're going to learn as a way of calculating the number of combinations. This is going to be n over r. And that n over r is going to be called the binomial, for now anyway, the binomial coefficient. Pascal's triangle has other applications, but Pascal's triangle, the expansion of that triangle, which even if you didn't realize what was happening, a plus b to the first, a plus b to the second, a plus b to the third, and then so on and so on, that expansion of that binomial to a high power, at least in terms of basic formula when a and b are just, just that, an a and a b are an x and a y, that Pascal's triangle, each one of those numbers is a number from the binomial coefficient. And then we have a first term that has some kind of power applied to it. 4, 3, 2, 1. Binomial to the fourth, the first power is 4. Binomial to the fifth, the first power is 5. The binomial to the sixth, the first power is 6. And that power of 1, 2, 3, 4, 5, 6 in the formula is identified as n. That's the upper limit of your sigma. That is where the power on the first term begins. And then you start taking away some other letter, like 4 minus 0 is 4. 4 minus 1 is 3. 4 minus 2 is 2. 4 minus 3 is 1. And 4 minus 4 is 0. So we're going to have an n minus r as our coefficient, as our exponent on the first term in the binomial. And that second term, the a plus b is our formula. We have a b to the 0, b to the first, b to the second, b to the third, b to the fourth, b to the r. Now, every sigma notation needs a what? What's at the bottom? A lower index, a lower limit. And what's at the top? An upper limit, in this case an n. So our lower limit is going to be r starts at 0, right? Because there's no b in the first term because that's b to the 0. There's no b in the first term because that's b to the 0. Or the sort of fourth power line that I've sort of expanded out for notes, that's 1, a to the fourth, b to the 0. Of course, there's no reason to write b to the 0 because anything to the 0 power is 1. We're just identifying this to show you the pattern of the binomial theorem. And that is the binomial theorem. Now, I will create Pascal's triangle to do a full expansion of a binomial for nearly all textbook problems, unless you have just some stupidly high power applied to the binomial, because it's super fast to build out. I mean, 1, 5, 10, 10, 5, 1 are the sort of base coefficients for a binomial raised to what power? 5. And look how quickly I built out that triangle, right? You can build it out super quickly. But there will be some questions that you definitely do not want to build out an entire Pascal's triangle for. And when that's the case, how do you find the third coefficient when a binomial is raised to a fourth power? Like, what's this binomial coefficient formula that creates all of these individual numbers in these rows? That binomial coefficient is equal to n over r times n minus r. Woo! Or in other words, n factorial over r factorial times n minus r factorial. That is your binomial theorem. And some questions you will want to use it, and some questions you would much prefer to just do use Pascal's triangle for that expansion. We have expand 2x minus 3y to the fourth power. Okay, I want to do this. I want to expand that binomial, and I obviously do not want to write out 4 binomials and start doing all that distributive process and adding like terms, and because it would take a lot of work. So I'm going to identify a as what? What's the first term? 2x. What's b? Remembering that the formula is a plus b to the n. Negative 3y. And what is n? 4. So to do this expansion, because the power applied to the binomial is only 4, I would go, okay, Pascal's triangle. Power of 0, power of 1, power of 2, power of 3, power of 4. Of course, if you write Pascal's triangle once on your homework somewhere, you don't have to keep drawing it over and over again, right? But there is our n equals 4 row. So the expansion of 2x minus 3y to the fourth can be started with, well, there's a basic coefficient. We're not going to end with that because there's other stuff going on. But 1, 4, 6, 4, 1. Okay? My first term is 2x. My first term is going to have powers starting at n and going down by 1 until it disappears. So we have 2x to the fourth, 2x to the third, 2x squared, 2x to the first, and then it's going to be 2x to the 0 power, no reason to write that. Our second term of negative 3y, I hope I left myself enough room. Negative 3y is going to first have a power of, what was it? 0. So we have that, I'll write this for notes. Negative 3y to the 0, then negative 3y to the first, bless you, negative 3y squared, negative 3y to the third, and then finally negative 3y to the fourth. And of course, we have that sigma notation creating an addition between all of these terms. The expansion is done. I mean, I have to clean things up, but what's 2 to the fourth? 2, 4, 8, 16. So we have 16x to the fourth, and anything to the 0 power is 1. So over here we got 4. A little bit of scratch work. We got 4 times. What's 2 cubed? 8. Negative 3 to the first is negative 3. All right, so I wrote plus, but it's going to be minus. So what's 4 times 3? 12 times 8 is 96. So negative 96 x cubed y to the first. What's 2 squared? 4. So we got 6 times 4. What's negative 3 squared? 9. This one might be a little bit tougher. What's 6 times 4? 24. Times 9. What's 9 times? Ooh, nice. What's 9 times 20? 180. What's 9 times 4? 36. What's 180 and 36? 216. 216 x squared y squared. Sorry for standing in front of you. What's 4 times 2? 8. What's negative 3 cubed? 3, 9, 27. Okay, I know it's negative, so negative. What's 8 times 20? 160. What's 8 times 7? 56. So what's 160 and 56? 216. X to the first, y cubed. The camera's just going to have my arm coming out of nowhere. Negative to the even power? Positive. What's 3 to the fourth? 3, 9, 27, 81. There's your expansion. Nowhere did I ever obviously use the binomial coefficient, but the expansion of Pascal's triangle, every single one of these terms does come from the binomial expansion. So let's do something that isn't a full expansion. What's a third term of the expansion? 3x minus y to the 21st power. Okay? I do not want you writing out 22 lines of Pascal's triangle. And you might still go, well, I can get to 22 lines pretty quickly, and the third term is only 3 terms in. But maybe I ask you for like the 17th or 18th or 19th term, something like that, where we're getting close to the right-hand side. Like here, because I'm asking you for just a specific term, you definitely do not want to do a full expansion. You want to use the full-blown, like exactly don't take any shortcuts. Get this formula memorized and work through that binomial theorem. And don't find the full expansion, just find one of them. So in this example, what is A? 3x. You can just call these out. What is B? Negative y. What is N? 21. And now, we haven't, I pointed it out, but what is R? Trying to give me an answer of 3, but he's wrong. Where does R start? Did we have a b in this fourth line of this expansion here? A plus b to the fourth, I guess b the fifth line. A plus b to the fourth. Did we have a b in our first term? No, because it was b to the 0. In the sigma notation, what does R start with? 1? 0. 0. 1. 2. For the third term, R is not 3 because R starts not at 1 but at 0. So R is 0 for the first term, R is 1 for the second term, R is 2 for the third term. Did I say that all correctly? So for the third term, R is 2. R is sort of the term number minus 1. This is your term, right? With a bunch of pluses in between each of the terms. So it's pretty straightforward at this point. You might not realize it. The binomial coefficient, N over R. We're also going to use the exact same formula later when we're talking about combinations. This is a number of combinations of a certain number of R successes out of N trials. What's N? 21. What's R? 2. What's the first term? 3x. And what power does it have? N. So 21 minus R, which is 2. No, we're not going to be doing what, we're not going to actually figure out what 3 to the 19th power is. Don't worry. What's the second term? Negative y to the what power? R power, 2. So this combination formula, this binomial coefficient formula, is 21 factorial, I won't yell again, over 2 factorial times n, 21, minus r, 2 factorial. That's your binomial coefficient. These parentheses now are just grouping symbols, not part of this combination formula. Times 3 to the 19th power, x to the 19th power. And what's negative 1 squared? 1, so y squared. So what's 21 minus 2? Of course, that's what? 19. So 21 minus 2 factorial is 19 factorial. What is 21 factorial over 19 factorial reduced to? 21 times 20. So we got 21 times 20, and then 19 factorial and 19 factorial cancel out, over 2 times 3 to the 19th, x to the 19th, y squared. Everything okay? Yes. Other than just some annoyingly big numbers. 20 divided by 2 is 10. Times 210, or times 21 is 210. Times 3 to the 19th power, x to the 19th, y squared. And that is your third term of that expansion. This is not in your homework. And granted, we do have 3 choices of mathematic tracks to follow after this. And I don't know if this is in all 3, but it's definitely in 2 of them. Find the term independent of x. And you have the binomial expansion or the binomial of x plus 2 over x squared to the 12th power. What does independence mean? It's on its own, doesn't care. Like, I want the term that doesn't care what x is. I want the term that's not going to change based on the value of x. What's the only way I'm going to have a term that doesn't care what x is? I want the term that doesn't have an x in it. I want the term whose value is independent of x, that no matter what I make x, it will not change. Why? Because there's no x in it. So what's the only way, since there's an x in each of these terms, what's the only way that we can have a term with no x? What does the exponent need to be? 0. How do we find each term in the expansion of x plus 2x to the negative second power? I just brought the x squared up out of the base, out of the denominator. How do I find what's the formula that gives me every term in this expansion of x plus 2 to the negative 2 raised to the 12th power? This binomial is an a plus b times n, right? How do I find what formula would give me every single term in this expansion? His hand is up right away. Go ahead.
It's just binomial theorem, right?
Yeah, bro. Just binomial theorem. So what is A?
Move out of the way. A is x.
X. What is B?
2x negative squared.
2x to the negative 2. What is N?
12.
12. And what's R? Well, that's kind of arguably the question. So we've got a coefficient, which we'll have to deal with later, but we can write this out. What's the binomial coefficient? N over R. Do we know what N is? Yeah, Liam just told us. N is the power. Power! 12. What's R? From this, we don't know. What is the first term in this expansion? What is our A? X. And the x has an exponent of 12 minus r. What is b? Right? There's a binomial coefficient. There's a first term to a power and the second term to a power. That makes up your three factors. I'm trying really hard. Keep with me. So what's b? You're just tired.
2x to the negative second.
2x to the negative second. What's the power on that? Wrong. R. It's n over r times a to the n minus r power times b to the r power. So it's the first base of x to a power of 12 minus r. Stop doing that. It's the 2x to the negative 2 power raised to the r power. And we need a term that has an x to the what? 0. What part of this involves the base of x? The last two. So we have x to the 12 minus r times 2 to the r, which arguably is not really necessarily part of this. 2 to the r times x to the negative 2r. That has to be equal to x to the 0. What part of this deals with the x? The first and last factors. So let's color code this. We're going to ignore the 2 to the r for a minute and focus on x to the 12 minus r, x to the negative 2r, and x to the 0. When you multiply like bases, what do you do to the exponents? You add them. So that's going to be x to the 12 minus r plus negative 2r is equal to x to the 0 power. So this exponent has to equal this exponent, or 12 minus 3r has to equal 0. Stop giving me the final answer. It's the process, man. It's a process. And now we're going to add both sides by 3r and get 12 is equal to 3r. And then finally r is equal to
4.
Woo! 4. Now we know what r is. Whoop, whoop. Yay, happy days. And now that we know a, b, n, and r, all 4 parts, I know I lost you. We're staring out in the middle of nowhere. What variables are in each of these terms? N, R, A, and B. You're going to have this on a test. You better pay attention. You mean you haven't taken these notes down?
No,
Oh, I said it was on a test. You know, if I write this on the board, anything I write on the board can show up on a test. That's why y'all, might have not liked my teaching so much first semester. All right, so what do we have? We have not 12 over r, but 12 over 4. Not x to the 12 minus r, but 12 to the 4. Not 2x to the negative 2, but 2 times, not 2x to the negative 2 to the r power, but 2 times x to the negative 2 to the 4th power. And we need to make sure that there's no x, so let's not assume what happens. Let's actually do the work. We have 12 factorial over 4 factorial, doing that binomial coefficient, times 12 minus 4 factorial times x. What's 12 minus 4? 8 times 2, bless you, to the 2 to the 4th, good catch there, 2 to the 4th, x to the negative 8th power. Okay. When you multiply like bases, what do you do to their exponents? Add them. I guess I should write that down. So we have 12 factorial over 4 factorial times 8 factorial times 2 to the 4th times x to the, yay, 0 power. Which means we've got, what's 12 factorial over 8 factorial? What cancels out? 12 times 11 times 10 times 9 over 4 times 3 times 2 times 1 times 2 to the 4th over 1. I love working with factorials because there's a bunch of cancellation. What's 4 times 3? 12. 12 divided by 12 is 0. What's 2 to the 4th over 2? 2 to the 3rd. So we've got 11 times 9 is 99. 2 cubed is 8 times 10 is 80. And that, right off the top of my head, just kidding, comes out to be, Paul, what's this equal to? 7,920. Oh, I'm so sorry. You got to get your notes back out. No, we've already learned how to take these complex numbers and convert them into polar form and raise them to a high power. I'll put a link to that video in the description below. And that's fine. And really, it is the most efficient way of taking complex numbers and raising them to high powers. But what if you don't have that high of a power and you don't have any technology, which in today's world seems kind of crazy to even say, but you don't have any kind of technology to find the argument, you will, for this complex number, the angle that will take you into the direction of theta that match in polar form, of course, that comes from this complex number in rectangular form. Well, you can come back to this idea of the binomial theorem along with remembering that, well, let's see here. I is equal to the square root of -1. I squared is going to be equal to -1. I cubed is going to be negative I. And then I to the 4th power is going to be -1 times -1, which is +1. And remember, your little cycle here, your 4-step cycle of taking I and raising it to a power of 1 through 4. And then obviously you can continue this pattern as we've discussed earlier into a power of 5 and power of 6 and power of 25 or whatever you want. Here identify that A is equal to 2. B is equal to -3i, and our n is equal to that 4, and work off along with this. Actually, we don't really necessarily need to do this. I'm not going to do a work with the binomial coefficient per se and our full-blown binomial theorem for an expansion to the 4th power. I'm just going to work with that Pascal's triangle, which I've now erased, and where we have the coefficient of 1 for the binomial to a 0 power, a binomial to the 1st power, 2nd, 3rd, and then finally when n is equal to 4. So our sort of beginning coefficients here for 2 minus 3i to the 4th power from the Pascal's triangle is going to be 1, 4, 6, 4, 1. Our first term of 2 is going to have, our a value is going to be 2 to the 4th, 2 cubed, 2 squared, 2 to the 1st, and then just for notes, 2 to the 0 power. Our b of -3 is going to initially have, or -3i is going to initially have that power of 0. And then -3i with a power of 1, -3i with a power of 2, and then -3i to a power of 3, and -3i to a power of 4, sigma coming through and creating an addition of all 5 of these terms. And now I just have to simplify this, combine like terms, and I'll have my 2 minus 3i, my complex number, raised to a power of 4. So for our first term here, we have a 2 to the 4th. So 2, 4, 8, 16. Anything to 0 power is equal to 1. Let's do a little bit of scratch work here. We have a 4 times 2 cubed. Well, 2 cubed is 8. So we have 4 times 8. And then we have a -3 to the 1st, or -3, and an I. So 4 times 8 is, of course, 32. And 32 times 3 is going to be 96. Of course, it's minus, so we have a minus 96i. Double check, yes. Our next little bit of scratch work here, we have 2 squared is 4, times 6 is 24, times -3 squared is going to be 9, so 24 times 9. And we have an I squared, but of course, I squared comes out to be -1. So we have 20, right, times 9 is going to be 180. 4 times 9 is 36. So 180 and 36 is 216, but there's a little -1 there from the I squared, so -216. A little bit of scratch work for our next term. So we have a little bit, we definitely have some work here, but we didn't need to use a graphing calculator or a scientific calculator to find the angle, again, that goes along with that complex number in rectangular form, or the argument. We're going to have -3 squared will be -27. We got our 4 times 2, which is 8. And our I cubed is -I. So of course we have a negative times negative is positive. We're going to have an I in this, this term here. We got 8 times 20 is 160. We have 8 times 7 is 56, and 160 and 56 is 216 again. And with the I cubed giving us again that -I, we have a negative times negative is a positive 216i. For our last term over here, we have 2 to the 0 is 1. We have negative 3 to the 4th is going to be negative 3. Well, a negative number to an even power, of course, is positive. So in terms of 3 to the 4th, we have 3, 9, 27, and 81. So we have a plus 81. Now let's make sure here we have an I to the 4th. Well, I is negative 1, so I to the 4th is negative 1 times negative 1, which is our positive 1. Now we just need to kind of like add some like terms. So let's see what we have here. We got 81 and 16. Those are both positive. So 81 and 10 make 91, plus 6 is 97. We got a minus 216. We got some like terms with some i's here. So we've got negative 96i plus 216i. Okay, so 210 minus 90 is going to be 120, but really it's 126. And 126 minus 7 is 119, but this larger number is actually negative. So we're looking at negative 119. Double check, yes. Again, we have 216i and minus 96i. So 200, let me just drop the 6 temporarily. 210 minus 90 is going to be 120, but it was 126 minus 6 is going to be 120 I, and that is our complex number of 2 minus 3i raised to the fourth power comes out to be negative 119 plus 120i, also in rectangular form by using the binomial theorem. I'm Mr. True. Bam! Go do your homework.